Hello, everybody. Am I audible?
Can hear you loud and clear.
Okay, thank you. Okay. I did realize that the clarity of the board got a little improved since I closed the window right next to it. So hopefully today it should be a lot better than last time. Some of the things that are due, we have a quiz before every lecture. And one is due January 19th, that's Wednesday, 1 week from today, and it is due right before the so it's 10 a.m. And there is a midterm. It's relatively far. We don't have to worry about it now. Let me mute everyone. Okay. So last time we barely started on introducing what an electric charge is. So electric charge, let's say. Interestingly, electric charge, there is a least amount of charge that appears on any of the particles that we have seen as of now, and that is called the quantum of electric charge, and this is E as a symbol used for that. So that's 1.60 into 10 raised to minus 19. Like we said, this is the amount of charge that's there on an electron. So this is measured in Coulomb. So O-U-L-O-M-B. So that's a new unit. It's one of the basic unit. Earlier we have seen the units of mass, length, and time. And now there is a new unit. It's the charge. So that's one of the basic units. Everything that we have come across as of now can be expressed in terms of three units that I mentioned just now: the length, mass, and seconds. But now electric charge cannot be expressed in terms of that, so we need a new unit, and often we just say this is Coulomb C. The charge on an electron, so electron charge, is equal to negative E, so it is negatively charged, and the proton charge on a proton is positive E, the same amount and exactly same amount. That's why an atom which is built out of electrons and protons is neutral, because these two add up to be 0. And this is, to our knowledge, this is exact to all the decimals. Like, it doesn't matter where you truncate your value. Here I have written it in terms of 3 significant digits. Even if you were to keep it to 10 significant digits, even then they cancel out exactly to our knowledge. Neutron is neutral. Neutron is 0. And interestingly, remarkably, every charge that we come across is in multiples of this. It never happens that you have 1.5 of an electron charge or 3.7 of that. It's always multiples of that. So it's a whole number times this particular charge. So it makes it easier to realize how many electrons there are. If we know how much coulombs of charge a material has, you divide it by this amount of number of charge, and you know how many electrons or protons are there in the system. So that's good. So that's your electric charge, which is the basic thing we will be talking about here. But now we will be having materials around us, right? So we will have materials. And materials can be characterized by their so-called conductivity, how much of these charges are free to move around. So materials will be characterized by mobility of charges. That means to say that if you have a metallic object like gold or silver or copper, the charges that reside on it, they are very free to move. Given a chance, they would move so that energy is minimized. On the other hand, other materials like mostly insulators like plastic or wood and other materials, the charges are not free to move. And there is a whole hierarchy of these materials. You can have on one end a perfect insulator, on another end a perfect conductor, and all the materials can be grouped in that scale. Here in this course, we will talk about only two kind of materials. That's an insulator, and let's call it a perfect insulator. So perfect insulator and a perfect conductor. Here, charges cannot move. Charges are fixed. And in this case, a perfect conductor, charges are completely free to move. Let's say completely free in the sense there is no resistance at all, completely free to move. And that's all we will talk about. There will be very rare situations that we will be actually differentiating something in between, which is neither a perfect conductor or a perfect insulator. In this sense, we can now talk about objects, which is an insulator or a conductor, right? And from now on, we might not even say all the time that this is a perfect insulator or a perfect conductor. It just is understood that always we will talk about perfect conductors and perfect insulators. Okay, so how does this, how do we look into the interaction between the charges? The experimental observation has been, and that was primarily conducted by Coulomb. And so let's say Coulomb's law. Is that if you were to have any material, so it doesn't even matter whether it is spherical or not, but let me make it spherical. So let's say there is a metallic solid sphere, which could be 10 centimeter in radius. So that's a sphere. And you put in some positive charges. How do you place positive charges on it? You often notice that sometime in winter, when you're removing your sweaters, there is a small arc you might see. a spark might go away from your cloth into another metallic surface. That's pretty much a transfer of charge. Whenever you see lightning is an example of situation where charges are being moved either from the cloud to the surface of Earth or from the surface of Earth to the cloud. Those are all very dramatic situations. But just by rubbing something against another object, you can actually transfer some electrons from one material into the other. And one of them will get positively charged and the other one will get negatively charged. If you can have such a material that is positively charged, so basically you rub something like you take this remote, for example, and I just rub it with a sweater, and there is a good chance that there is a certain amount of charge on this remote. And equally, I must have lost that much of charge from me. So that's the simple way you can charge materials. And if you have such a material, the observation has been that if you bring in two such spheres, doesn't have to be the same radius, two objects, and it doesn't even have to be a sphere. If they are like charges, so positive and positive, right? They repel. So there is a force exerted by one on the other. And the same thing, according to Newton's law, that is an equal and opposite reaction. So that is a force acting in the other direction also. You can have two negatives. So this is case one. Let's say case one. There could be another case that you have two negative charges. And again, it turns out that they repel. So there is a force that acts on this, and let me say it's a vector force, and we would like to know what this force is. Right? That's our goal. Yeah, or that's what Coulomb tells us. Let's put a case 3. There is also a possibility that these two charges need not be the same. And once it is not the same, it doesn't matter whether it is positive or negative. I can keep either one of them. So in principle, there are 4 cases, but the third and fourth case are in a sense identical. So that's a positive charge, and there is a negative charge. And in this case, it was noticed that this force is attracted. And again, because of equal and opposite reaction, so there are two forces, one exerted on the other. It's like saying this charge pulls the other charge, but then the other charge also has to pull the charge in the opposite direction. So that's often we say that like charges repel and unlike charges attract. Unlike charges attract, like charges repel. We would like to know now that what is the force acting on this? What exactly is the equation, or what exactly governs this force? So let's say this is 1 and that's 2. So this is the force on 2 by 1. So let's say this is on 2 by 1. Right? That's a notation I've created, on the charge 2 by charge 1. Here, similarly, this will be on 1 by 2. Right? That's your force. Same thing happens here. So this is number 2, that's number 1. So this is 2, 1, that's 1, 2. And same thing, this is 1, 2, that's 2, 1. And we would like to know what exactly is this force. It is determined in terms of the charges, how much charge is there on this and the first charge. So let's call that Q1 and Q2. So there is Q1 amount of charge on the first charge. It could be 3 coulombs or 3. Coulomb typically is a very large amount of charge. Typically, we come across charges in microcoulomb. Microcoulomb, nanocoulomb, that's the typical charges that we see around. If we, whenever we have a electrostatic a spark that comes off from our sweater, we are talking about probably a nanocoulomb. Like nano is 10 raised to minus 9, a very small amount of charge. But the idea is that small is always relative. Micro is the maximum amount of charge we will see. If it is 1 coulomb of charge, that's too much of charge. It might just break down everything around it. Like air breaks down very easily. That means to say that lightning kind of situation can happen. So 1 coulomb is too much of charge. Microcoulomb, 10 raised to minus 6. That's what a microcoulomb is. That's typically that we see around it. So let's say that is Q1 and Q2 in that way. And the idea is, what does the force depend on? It is realized that it is proportional to these charges. That means if the charge is large, the force is large, and it is inversely proportional to the distance between the charges. So let's say there is a distance between them. So let's say this is R. So that's your, there's a vector in principle, but let's say if we are interested only in this distance. So that's R. That's the distance R. And the force acting on these charges, according to Coulomb, is F21, let's say, is equal to, it is proportional to the charge Q1. It is proportional to charge Q2. And it is inversely proportional to the distance square. So it's R square. That's the formula that Coulomb realized, that it is proportional to the charges and inversely proportional to the square of the distance. Remarkably, it does not depend on the radius of the sphere. It doesn't matter whether it is a small sphere or a big sphere. And then the confusion comes, okay, if it doesn't depend on the radius, what does this R mean? That means it is from center to center. Right? This distance R is measured from the center of the object to the center of the other object. If it is spherical, that's clearly, it's very clear as to what that point is. If it is not spherical, then we have to define what is called a center of charge, exactly like center of mass. But we will always work with spherical quantities, so we won't have to introduce that idea. So the center of the sphere is where the distance is measured, and you go into the center of the second sphere. There is also one more point, that this is a vector on the left hand side, so there should be a vector on the right hand side, and that will be represented by a symbol R hat. And that means that R hat is just a symbol saying that it's a vector in this direction. Instead of specifying exactly what that vector is mathematically, you use a symbol saying that this is pointing away. So draw a line between the two charges, and it is pointing away from the charge. If it is both positive, if it is positive and negative, then it is again along the line connecting the two charges, but towards the other charge. So this R hat represents that vector, whatever that vector is. There is one more quantity that comes in, that is to experimentally or dimensionally fit in. That is, force does not have any Coulomb in it. So we have to compensate for the dimension Coulomb that appears on the right side somehow. So that's we put in a constant there. So this is often written as 1 over 4 pi epsilon naught. That's a Greek symbol with a subscript 0 on it. Later, we will see that this describes the property of the material in between, in this case, the vacuum. So that's epsilon naught. So that's a constant completely. And epsilon naught is equal to 8.85 into 10 raised to minus 12. That's a number. And now we need to get the units straight. The units are in such a way that it compensates for this Newton and the Coulomb. So this is Newton meter square over Coulomb square. So there's a Newton meter square that goes on the left hand side and divided by Coulomb square. You will notice that we will, at least in the first few weeks, we will always have this 1 over 4 pi epsilon sitting in front, and it becomes a burden to always do the calculation. So it is good to give this whole 1 over 4 pi epsilon a number, and often that's what you do. So this k you call a constant k, which is 1 over 4 pi epsilon naught. You multiply 4 pi with this and take the inverse of that, and that's equal to 8.99 into 10 raised to 9. And you have to flip the units, right? In this case, so this is Coulomb square over Newton meter square. So the idea is, again, what is Coulomb's law? If you have two charges, there is a force acting on either of the charges, and that's given in terms of what is called the Coulomb's law. It is proportional to the charges and inversely proportional to the square of the distance between the centers of the charge, and that is a constant multiplying that gives you the units correctly. That's a new force that we have come across all through the first semester of this course. We worked with various forces, and that's a new type of force we have, which is called the electrostatic force. And now let's do some examples very similar to what we did in the earlier semester. If there is one force, we can have many forces and they add up vectorially, right? And in principle, mass times acceleration using Newton's law is equal to the sum of the vector forces. So if we know the forces, we can actually talk about what's the acceleration of this charge. So let's do an example related to that.
Excuse me?
Yes, please.
On the K down there is when it goes to the C, Coulomb, is that a 1 or a 2?
2, Coulomb square. This is the inverse of this. So let me write this again here.
Okay, thank you.
So let me write this again here. So that's K is equal to 8.99 into 10 raised to 9 Coulomb square over Newton meter square. Okay. It's good to give some meaning to this. This is meaning or the definition of epsilon naught is. We won't use it so much until about 4 weeks or so. This is called the permittivity. Permittivity of vacuum. Okay. What that means is that this is an electric property of the medium between these two charges. We are talking about two charges in air. Air is pretty much like a vacuum, but let's say it is a perfect vacuum, and the vacuum's property is 8.85 into 10 raised to minus 12. If you were to put in any other material, like say plastic or wood or mica sheet, that's typically having a good amount of electrical property in it, then these numbers change and they can be significantly different from these things. Most of the time, we will work with vacuum, and there will be very rare situations, of at least I think only one section or so, somewhere around the 4th week, we will talk about some material properties of or the permittivity of a material instead of a vacuum. Okay. Any questions? Okay. So let's have a situation where there are more than one force acting, and our idea would be to calculate the total force, right? So let's do that example. We have two charges here. Let's have three charges, right? And where you place some matters. So let's say, so that's a coordinate system. This is your X and that's your Y. Let's say. And let's have three charges placed here. So let me place one of the charges on the origin itself. And let me say that's a positive charge. So it's a positive charge, and let me call that Q1. So Q1, let's say, is 1.0 microcoulomb. So this is, you typically say this is microcoulomb. What that means is that that's 1.0 into 10 raised to minus 6 coulomb. That's one thing new that you start working with all these small tiny numbers, and you have to carry out this exponents with you. And that's probably you did not see too much in the earlier course, but we will get used to seeing it. So let's say we have Q1 there. Let's put the second charge somewhere here. Let me say that's negatively charged. So that's Q2. And this was positively charged. So let me specify that as positive. Q2, let's say, is minus 2.0 microcoulomb. Right? Again, it means minus 2.0 into 10 raised to minus 6. Let's say I keep a third charge here. So let's say third charge, again, let's say that's negative, and that's Q3. And let me say that's minus 3 microcoulomb. Let's also have the distances given to us. So let's say this is A and that's B. If you have these kind of this amount of charges, this is very close to what you see on an electrostatic. Whenever there is a spark in the around in the air happening, that's the kind of distances or charges you're talking about. So let's say A is 10, A is larger, right? So let's say A is 15 centimeters and B is 10 centimeters. And this decimal here means that it is known to second decimal. So this is, if I don't put that decimal sign there, it means that there is an error in the zero. So it's only one significant digit. So this clarifies that there is two significant digits. If I know A and B, I also know the distance between 2 and 3. So I know all the distances that is necessary in here. And let's ask the question, determine. So the question could be determine the total force on Q1. So that's Q1 here. So Q3 exerts a force, Q2 exerts a force. Let me also say the total electric force, because you might wonder, oh, what happens to gravity, right? These are spheres. If you leave it as it is, if it has a mass, it will experience a gravitational force or other forces. So let's clarify that we are only interested in the electric force. That means to say Q3 exerts a force on Q1, Q2 exerts a Q1, and similarly, all three of them exerts a force on each other. So let's see what are the forces. Let me draw them again here. So this is positive, that's your negative charge. So that's 3, that's 1, and you have a negative charge here. I'm interested in charge Q1. So that's the charge I'm interested in. So let me start with 2. 1 cannot exert a force on itself. Force is always exerted by another entity. So 2 exerts a force on 1. These are oppositely charged. So that means it will be attractive. So there will be a force in this direction. I have to give it a label. So that's F. We said on 1 by 2, right? So this is on 1 by 2. So that's the F12. That's the force due to 2 on 1. Same thing happens here. 3 tries to attract 1. So it will pull it towards that. So, and this is slightly closer. So there's a chance that this might be a larger force, right? So you don't, it's an interplay of distances and charges. So you shouldn't conclude that immediately, but it seems like probably this might be larger. So this is F13. So this charge 1 gets pulled towards the right and towards the top. So the total force will be somewhere along the diagonal, right? And we would like to know what's that total force. That's what we have to determine. And if we know that total force, that will decide how much it accelerates, right? Using Newton's law, mass times acceleration is force, and that will determine how much it accelerates. So let's see what is F12. So F12 is equal to, it's clear here that this is along the X direction, right? So the problem has been constructed in such a way that all the forces are either in the X or Y direction. That need not be the case. We will come back and do such examples later. But in this case, we know that this is in the horizontal direction. So when I wrote R hat earlier in Coulomb's law, now I know that this is I hat and this is plus I hat. So that's a direction of this force. And then there is a number there, which I have to calculate. And that's determined by Q1 times Q2 times the distance between 1 and 2, that's A. Right? So that's A squared. And we have to put in those numbers to calculate that. But before we do that, so typically the force has an X component and a Y component. So this I hat simply means that it's in the X direction. It is just a symbol that tells us that the X component is this. What is its Y component? It is 0. So there is a X component and a Y component. Y component is 0 in this case. Same thing happens with F13, except that now the I component is 0. It's purely in the vertical direction. So it is I hat is 0 plus J hat. It is plus because it is in the positive direction. It's pointing upward along the positive Y-axis, plus J hat times K times Q1 times Q3. And the distance now is the distance between 1 and 3. That's B squared. Okay. It seems like overwhelming. That's an equation with too many variables. But if you put in numbers, it becomes very straightforward. So let's calculate this number right away. So okay. Okay, so let's get this number. So we have K Q1 Q2 over A squared. So that's equal to K, we said, is 8.9, or if we are in 2 significant digits, because I gave the charges only to 2 significant digits, I need to keep only 2 significant digits. So that's 9.0 into 10 raised to 9. That's K. Q1 is 1 into 10 raised to minus 6. Q2, you would say, is minus, but 2.0 into 10 raised to minus 6. Notice that instead of keeping the negative there, I have already taken care of the negative when I took care of the direction of the force. 2 like charges attract and 2 like charges repel and unlike charges attract. When I use that idea to write down these directions of the forces, I've already used that fact. So here I don't have to use that. So to clarify that even better, let me say this is magnitude. That's magnitude of Q1 and magnitude of Q2. So ignore the sign when I'm actually putting it as numbers in there. Divided by A squared. A is, we said, 15 centimeters. So that's 15 into 10 raised to minus 2. We need to put it in meters, right? So that's square. You can do this in various ways. Many of you might have, you might be familiar with putting this into the calculator itself. That's one way of doing. Sometimes, at least I like to do these numbers separately. So I say 9.0 times 1.0. right? I'm putting all the numbers in front first. And then that is 15. Do not forget the 15 square. That's 15 square. I put those numbers separately, and the powers can just add up. So that's a plus 9. That's minus 6. Again, a minus 6. And then in the denominator, that is a minus 2 times 2, that's minus 4, which in the when you take it to the numerator, that becomes a plus 4. That's relatively easier to handle. And that comes out to be, I need a calculator. Give me a second. So put this, so that's 9 to 18 divided by 15 square, and that's 0.08. And since I need two significant digits, I put a 0 in the end. And this is 9 plus 4, 13, 13 minus 12, so that's 1, right? So that's 10 into 10 raised to 1. So that makes it 0.80 to 2 sig digits. This is in newtons, right? So this is newtons. And since this was the first time we put in numbers, I went slow, but very soon we will start going faster on this. The other number we need is Q1 times Q3. Again, I put the magnitude in there, divided by B squared. And this one is pretty much the same as far as the powers goes. It's just these numbers that change, right? It is 1 and 3 and divided by 2. So if I were to do that, so this will be 9.0 into 1.0 into 3.0 divided by 10 square, and the power remains the same. So that's 10 raised to 1. And that comes out to be 27 divided by 100. So that's 0.027, and that's 0.27 newtons. Clearly, the 1 and 3 is between 1 and 3 came out to be smaller. And why is that? Did I do this correct? 9 into 327, 0.27. No, this is 2.7, right? Yeah. So this is 9 into 327. 27 divided by 100 is 0.27. So it is 2.7. Why I suspected that was that if you look at the excuse me. Why I suspected that was that the force between 1 and 3 seems to be larger because the charge is larger, relatively speaking, and the distance is smaller. When in the denominator, the distance is smaller, it should be larger. So that's why I suspected it, and I think this is 2.7 Newton. Okay, so that's your numbers, but we still have to work out the magnitude and direction. So let's go back, let's say, so let me say this is F12, right? So that I can erase a few things. Yeah. Okay, so if I were to use these things, I have F12 is equal to I hat times 0.8. Let me drop the units. It's understood that it is in newtons, so that there is less clutter in that sense. And then this is J hat times 0, right? And it should be 2 significant digits, so I should put in that 0.80. F13 similarly is I hat times 0 plus j hat times 2.7. Again, it should be newtons, but I dropped the units so to avoid some clutter. Okay. We are interested in the total force. And when we say total force, we should have both a magnitude and direction to that. So I just have to add these two forces. So if I were to add them, so the total force F is, when you have it in the X and Y components, they're very easy. They just add you just add the components separately. So this is I hat times 0.80 plus j hat times 2.7. And that's your force if you want in component form. Where does what's the direction of this force? If you were to visualize this, that's approximately 3, and that's approximately 1. So it's smaller. No, the X is small, right? X is smaller, so let's see. 1, 2, 3, right? So this will be down here. So the force will be something like this. That's your F total. But often you're interested in what is the magnitude of this force. That means what is the length of this force, and by direction, we mean what is the angle it makes with respect to some direction. So let's choose X as our reference. So we can say when we want to specify what's the direction of this force, we can say it is so many angles with respect to the X-axis, or we could say it is so many angles with respect to the Y-axis. Either way, you have to specify it, you have to remove the ambiguity part in there. So whenever you say direction, you have to make it very clear. So what is the magnitude? So magnitude is F total. So that's a vector. Magnitude is often represented by 2 lines around the vector force with the vector sign. And this is equal to the square of the X component. So it is basically this length here. So you're interested in the hypotenuse, so square this and take a square root. That's what we are doing. So that's 0.80 square plus 2.7 square. Must have done this sufficiently when you are adding forces in the first semester part of this. So this is equal to 2.7 square plus 0.8 square. Then take a square root of that. And that comes out 2.8 newtons. So that's 2.8 newtons. So that's the magnitude, but as I said, you have to specify the direction also, right? Direction can be this angle or this angle. So let me say this is angle theta, and the direction of this force is given in terms of theta. So let's say theta is equal to, if you were to have a right triangle here, I know this length and this length, so it is a tangent of theta is opposite over adjacent. So it is tangent inverse of the larger distance, 2.7 over 0.8. And that comes out to be. And again, when you're taking the tangent, it's in this case, it doesn't matter. There is no ambiguity there. But if you're in this quadrant, sometimes it is good to drop the negative sign. So visually calculate the angle theta that's less error prone. So you probably have come across those situations before also. Otherwise, ask me another time and I can clarify on that. So this is tangent inverse of 2.7 divided by, and that comes out 73.5 degrees, and to 2 6 digits, it is 74 degrees. But I have to clarify with respect to what, right? Whenever you say an angle, it is always with respect to something. So it is with respect, so you have to say it is counterclockwise, right? Or you can say it is north of east. So it is counterclockwise. Counterclockwise. Clockwise is this way, so you're going counterclockwise with respect to positive x direction. You can also say if it is 74 degrees from here, you could have calculated, someone else would have used this triangle to calculate that, and they would have said it is 16 degrees. It is also equal to, so direction can be also written as 16 degrees clockwise with respect to positive y direction. So either way, that's perfectly fine. There are various ways of saying this. You can say it is 90 plus 16 is 162 with respect to negative x-axis. Either way you say it, that's all conveying the same point. Okay. That's an elaborate, sufficiently long problem. But you have this in your homework. That's a primary, a long problem in the homework. I think it is the last problem in the homework. There you, like, this is relatively easier because it was in the x and y direction, right? There I asked you to calculate the force on charge 2 instead of charge 1. And we will come back and do those examples. But very quickly, I want to mention in the last 3 minutes, I want to mention one point about insulators and conductors. So let's consider two situations. We have insulators, insulators, and there is another situation where you have conductors. So here we have a positivity charge Q1, and that is another charge Q2. And the same situation in conductors. Now these are conductors, these are insulating materials on which there is a charge. And here again, there is a charge Q1, and this is positively charged Q2, let's say. Okay. Now we want to do identical things in both cases. What I do is I bring this together, I touch them. Right? So this is 1 and that's 2. Right? So I'm touching them. And do the same thing here. So that's 1, that's 2. And then I separate them again. Okay, so that's 1 and that's 2 again. And here again, it is 1 and that's 2 again. But now what happens is that insulators, the charges are fixed. There is no movement of charges. So how much charge is there on this? It's still Q1, it is still Q2. Touching doesn't matter because they are not mobile. Nothing happens in this case. But what happens here is that there is a Q1 and a Q2. This could be 1 coulomb, that could be 3 coulombs. They share, they move around, and that new charge will be Q1. So they will, if there is a positive and a negative, they will cancel out each other, and this will be Q1 prime is exactly equal to Q2 prime, and they share the charges. So that's Q1 plus Q2 over 2. Okay, and an example could be, for example, this could be plus 3 microcoulomb. This could be minus 7 microcoulomb. They cancel each other, minus 4 remains, and minus 4 divided by 2 will be minus 1 coulomb each, and that will be the charge on that. So that's a logical problem you can build, and there is a similar problem in your homework. Let me stop at this point. It's exactly 10:50, and thank you.
Have a good day.
Professor,
Yes, please.
what chapter are we on?
I think it is chapter 23. Let me see. since I teach more than one course, it is slightly, it is called electrostatics. Write me an email. I'll write to you about that. Okay. I think
Okay,
it's,
thank you.
I think it's chapter 23.
Okay, thank you. Have a great rest of your day.
Thank you. Okay, let me close.